Hej allihop och välkomna till det här webbinariet om CST. Björn Wallén heter jag jobbar som teknikchef här på SolidEngineer. Och tillsammans med mig har jag Hassan Schreim. Och nu kommer jag byta till engelska. Welcome Hassan.
Thank you.
We're so happy
Björn.
to have you here.
Likewise.
And we are very interested in learning more about
It's a pleasure.
CST. So before we dive in, can you explain in simple words what we mean by electromagnetics?
Sure. So basically electromagnetics, it's a composition of two words, electric and magnetics. And usually we are dealing with everything that, carry currents, even if it's a small battery or even an antenna, usually you send a signal and the signal circulates into the structure and then it gets radiated via what we call an electromagnetic fields. So this is the general term of electromagnetics, yeah. And you will see that we are having electromagnetics everywhere around us.
Yes, we certainly do. All right. There are many numerical methods out there.
Mm-hmm.
So why does CST use different solvers?
Sure.
And how do we choose between them?
Yeah, that's a very good question. Actually, as I said before, electromagnetics is a general term, but we can compose it into electrostatics, magnetostatics, quasi-statics, or even high frequency, low frequency, etc. So all those terms, I would say, are a part of the electromagnetics, and basically they're a kind of one numerical methods because we are solving different equations, right? We call them Maxwell equations,
Yeah.
and each part, or each application, it has a dedicated numerical methods, and this is why, since we cover all of those aspects, we have all the numerical methods that answers each application. Yeah. So we have, I think, more than 25 numerical methods inside the tool. Yep.
So that's a benefit.
Oh, definitely a benefit, yeah.
Yeah.
And they are all within the same graphical interface, so you don't have to switch from a tool to another tool. They are all there.
They're not
Simple
different
way.
programs in
Nope,
any way. They're
only
just
the one, yeah. CST.
Sounds great.
Yeah.
So CST is said to cover a very wide range of
Yep.
applications.
Mm-hmm.
Could you give us some concrete examples?
Sure.
Beyond antennas?
Of course. If you allow me just to go here to this. There we go. So if we have a look at this slide, actually we can divide our applications into 5 or 4 applications. First of all, we have the low frequency. By low frequency we mean studying all the devices that do not radiate the energy. The energy stays in the or around the structure. And then we have, of course, the microwave here and the RF devices. So here we are sending energy. For example, the antennas, it's used to send information from point A to point B, and without antennas you have no connectivity. So we call this kind of high frequency applications.
Yeah.
But there is something other than antenna. There are we call this the RF devices, such as filters. They are all used within the communication channel. Okay, so this is the high frequency market. Then of course we have the EDA, or the electronic market. So nowadays, if you open any electrical product, you find those green boards. And those green boards, what they are, they have traces in there, and they have components like CPU, memory, and those components, they communicate together, and they use the traces on the board to communicate info, to send and receive info. And nowadays, we are talking about speeds that exceeds 200 gigabits per second, or probably 400, 500 gigabits per second. And the more we go up in frequency and speed, the more the board becomes very complicated.
Yeah.
There you go. And this is why simulation is super important in this domain. Yeah. And of course we have here the electromagnetic compatibility. This is something super important because, again, if any company wants to produce a device that they want to put on the market, they need to certify it before. And if you want to go straight to the lab and measure this, you may have bad surprises, etc. So simulation helps with that because it actually predicts if your device will be certified or not. And finally, we have the most exotic domain, which is the particle dynamics. So here we are studying a little bit the interaction between the electromagnetic fields and particles such as electrons, protons. It could be even dust, because dust could be charged. And for example, we have a customer who is using CST to create cleaning devices of the dust. Yeah. It's a very niche domain, but the applications are super exotic and they are super amazing. Yep. So there you go.
Yeah, sounds exciting.
Yeah.
A lot of capabilities. So let's talk a little bit about HPC and cloud.
Yes.
So why do we need high performance or cloud computing for simulation?
You know, nowadays the products, they are becoming more and more complex. You know, usually in the past we used to do our design, you know, through with a cutter. We cut out the copper from electronic boards, but nowadays, you know, structure, they are getting smaller and they are getting more complex, and we are integrating more and more components inside one single device. Now, of course, you can run the simulation on a classic computer, but usually the companies, they want to obtain the results the fastest way possible. And this is why we introduced the HPC, or what we call high performance computing. And for this, of course, the user can have the choice between running this on his own machine, right? If he has the infrastructure, let's say, or we provide our cloud, you know, where we have lots of super powerful computers where the user, he can have access and run his simulation on our platform. Yep.
And that offloads sort of the
Yep,
from your
definitely.
computer
From,
as
yeah.
well, so you can keep using your
Exactly.
computer.
So the company may avoid, for example, investing in a supercomputer for simulation. They can use our cloud, and that's it.
Sounds excellent.
Yep.
What changes when we run a project on an HPC compared to a desktop? Is it just faster?
It's much faster, and we can get factors up to 10 times acceleration, of course, depending on the motherboard and all how the computer is configured. But yeah, regarding the simulation, we can go up to a factors of 10 times. And for companies that they are dealing probably with very high, or I would say very complex devices, and they have very, let's say, tight deadlines, this is super helpful. Yeah, that's for sure.
I can imagine.
Yeah.
So let's talk about antennas.
Let's.
Let's do that. So when it comes to antennas, what are the typical challenges companies face that simulation can solve?
Yep. So let me show you something here. So usually the first question we ask, where do we find antennas? And the most simple answer is
everywhere.
Indeed, they are everywhere. So if you look here, you can find them on aircrafts, inside cars, on wind turbines, of course inside mobile phones, because antennas are the keys for connectivity. And since antennas, they do not operate alone, so usually even myself in the past, when I was doing my studies, I used to simulate the antenna alone floating in the air, but this is a big mistake, because you have to take into consideration all the environment around the antenna, right? Probably you may have heard about this Apple 4 antenna gate. It has a problem.
I think I was affected.
Oh, there we go. You were one of the users that got affected, and I think since they, you know, there was a problem, because if the user was holding the phone in a certain position, they would lose the network. And this is because, you know, the environment of the telephone, which is the hand, was not taken into consideration as it should. And this costed $183 million to Apple, only to correct this, you know, between pieces and man-hour. It was very, very expensive, let's say. But yeah, this is why simulation is super important, because if we go here a little bit further, I'm going to give you just an example. This is a mobile phone, so you see we have at least here 6 or 7 antennas inside. So if you want to see how they operate or how they affect each other, you need to go through simulation. Otherwise, it's a nightmare. Yeah. And of course, you can see here that we have our numerical methods that are dedicated to, you know, every type of antenna could be simulated with a different numerical method, of course. I mean, it depends on the applications, of course, yeah. But we have them all included. This is the good part, yeah.
Yeah, so could you give us an example of how antenna, I think you did that, simulation can save development time or improve performance? Yeah, so Apple is a good example of that.
Actually, simulation, Bjorn, is always about predicting how the antenna or how the full device will operate. And if you are making sure, because usually what we are doing in the software is solving Maxwell equations, right? And if it doesn't work, it's either Maxwell is wrong with his equations, even though we are basing our studies for more than 100 years on his equations.
He hasn't
so
been wrong so far,
There you go. And since we are solving Maxwell equations, you know, the hard thing is to do that on a very complex structure. And what we do with the tool is that we divide those, and you know, you always avoid bad surprises with simulation. And you know before going into prototype, so you don't lose money, you don't lose time, and you have a very big ROI, because this is what companies are about, right?
Definitely.
So you invest in something that will help you to reduce time, reduce what we call the time to market. You know, this is very important KPI for companies. And this is what simulation helps for, to reduce this time to market and of course reduce it prototyping and cost, yeah, drastically even, you know, it's not like a very, like a little, no, it changes the life of a company. Yeah, it's a game changer, totally.
So how about compliance? So
Yep.
you mentioned that, regulatory compliance, it always seems like a painful thing to deal with.
Yep.
So how can simulation help us catch problems before we build prototypes?
So compliance, just to give you an, you know, a very important info, any company that would like, for example, to put a device into the market, it needs to be certified before. And even now, people, they are still going to the lab to measure directly. And even, I mean, until now, 50% of those measurements, they fail. So the company fails to meet the certifications. Whether it's, you know, it could be like in the US, we have the FCC. In Europe, we have the CE or we have the IEC. We have even military standards, because even the devices dedicated for defense application, they have their own compliance. They need to satisfy those compliance, right? The thing is, if you go to a lab and you measure your device and it's not, you know, it's not compliant, this is not even the hardest part. The hardest part is to find the reason. And since electromagnetics are invisible, we cannot see what is going on with our bare eyes. The simulation helps you with detecting, not even predicting if it's failing or not, but if it's failing, we can detect and we can see what is the origin of the problem, and this is how we can intervene into correcting the device, so it could comply with the standards.
So not only seeing whether or not it will work, but also why.
Definitely.
Why doesn't it
Why?
work?
Yes, exactly.
That's a huge thing.
So you can see here on the slides that compliance are not only about the device itself, but it's also about human. Nowadays, if you want to buy a phone, on the packaging of the phone, there's a value we look at. It's called the SAR, SAR, which means specific absorption rate. So in 2 words, it measures the power that is received by a human body, and it should not go beyond certain limitations, because if it does, again, your phone cannot be placed into the market. You have to recertify it to make sure everything will be fine. So this is regarding the human body, and even regarding, you know, even the device itself. For example, if we look here, we have those kind of products, and you see this is, for example, the lab where people, they go to certify. So it's a lab where you have an antennas that detects radiation, etc. And this is the kind of electronic products that need to be certified. So the thing is that we create what we call a virtual prototype. We put it into the software and we predict how it will be, you know, behaving. And of course, we have a lot of automatic workflows to make the life easier of the engineer, and to make, you know, it's in the company's interest, of course, to, again, it's always the same time, reducing time to market, reducing cost, and reducing prototyping.
Excellent. So how about, you mentioned PCBs being denser and denser. So what kind of electromagnetic issues show up, and how does CST help?
Well, for example, if we have a look at this PCB, it's a good thing that we have it still here. I mean, those PCB, look at the number of components that we have. Of course, you have capacitors, resistors, whatever you want. But if we take, for example, the electronic board of the computer, it has a CPU, it has memory, and all of those components, they communicate together, right? They send info and they receive info as well. Now imagine when the PCB gets denser, it means that the info, where it's sent from point E to point B, it will be quickly deformed. Like usually we send square signal, and you don't want this square signal to arrive like a triangular shape. Because, you know, it's zeros and one going over there. And usually we need to make sure that the signal is well received by the destinator, right? For example, if the memory is receiving info from the CPU, we need to make sure that the memory is receiving the good signal. And for this, eventually, we have a study, what we call the eye diagram. If we go just a little bit here, there we go. I think it's here, the PCB. Here we go. And as I told you, you know, the speed of sending those, it's becoming more and more high. It's higher and higher. And even in the future, we will have the 6G. So I think the frequencies in the 6G will be over the 300 gigahertz, which makes the speed the double, 600 gigabits per second, because 0 and 1. So this is very, very, I would say, complicated. And usually what we look for is this kind of, you know, this kind of KPI. This we call the eye diagram. And with the analogy of the human eye, the more this eye is open, it means the more you are compliant with that. We call this a signal integrity simulation. But we do have other types of studies that we call power integrity, and in the power integrity we make sure that all the components are working perfectly. So again, it's the optimization, but on the PCB. It's not an antenna, but it's a PCB. Even though antennas, they could be on a PCB as well.
Yeah.
So the doors are open for any innovation. By the way, innovation, it's also something very important for companies, because if you want to go with an idea, it's always better to predict it virtually before fabricating it. So it's not only about seeing if your device, but also about innovating and make your device more performant and make probably new devices.
Yeah.
So it opens the door for innovation. This is also a value that we cannot ignore.
Yeah, and that comes sort of back to not limiting yourself to right, this is working, but understanding why it's working and then being able to improve it even further.
Yep.
Yeah.
100%.
All right, so you mentioned 300 gigahertz, that was high frequency. So
Very high,
how
yeah.
about low frequency stuff?
That's
Right?
good.
Yeah.
So as
The
I told
other end
you,
of the spectrum.
yeah. As I told you, low frequency, if we go here, it's not like high frequency, because if we look at those applications, you know, you have the MRI machine here. It's not the phone we're speaking about, it's not the antenna, but it's more the charging. You know, because if you take the charger, for example, for the iPhone, or for even for any kind of phone manufacturer, now you have the induction charging.
Yeah.
So we call this the wireless power transfer. You know, you are sending energy without any wires. So when we speak about low frequency, it's always about devices that they do not intend to radiate the energy. So the energy, it's really around the device itself. So here's some applications. For example, we have those induction charger for cars, because they exist now. You know, now you have station for cars. Of course, you have the classic charging. You have the sensors that are on the phone, which are a kind of, you know, the screen, the touch screen. It's an electronic phenomenon. It's electrostatics. And we have one of the biggest applications, which is the motors, electrical motors. It's a big market for low frequency with the electrification trend that is happening now. So, so we are even, you know, intervening in what is related to, you know, to sustainability. You know, because electrification is in the way of making everything cleaner, right?
Absolutely.
And there you go. And of course, when we speak about electricity that you have at our home, this is low frequency as well. And this is why, for example, here on the screen behind you, there is a transformer. You know, transformer used to take a voltage, increase it or decrease it, you know, depending on the appliances you have at home, etc. So all of those applications, they are a part of the low frequency. So we can also cover that.
Impressive.
Yep.
All right, so maybe time for a little wrap up.
Yep, sure.
So if we look at the bigger picture, so how does all of this translate into a business value for a company?
Sure. So as I was saying in the beginning, a company, you know, usually you need to invest somewhere to find it somewhere else, right? And the idea is to, we are here to help the company to get to their objectives the fastest way possible. I mean, we are even noticing nowadays, every 2 days you have a startup company that comes with an amazing idea and they want to put it in, you know, they want to make their dream a reality. So first of all, we help companies to transform their ideas into values, because, you know, they have an idea and we help them to create and to concretize this idea. This is from, let's say, from an innovation point of view. But again, imagine if you want to get into a race with your competitor, right, with your competitors, and you want to be the first one to create a device, you know, a specific device. This is where we can also help. This is a very big value, which is the time. Time is money, right?
Time is money.
And people, they want to reduce the time, reduce the cost, which will increase the revenue of the company. So the value that, you know, we have as engineers or as a software provider aligns 100% with the value of a company, because we have the same objectives, you know, helping the companies to get what they want when they want. So we see we have the notion of time, but we have also the notion of cost, and we tend to reduce those and to make the company's life easier. Yep.
That sounds good to me. All right. I think we're running out of time.
No problem.
So thank you very much,
Thank you,
Hassan, for joining us.
It's a pleasure.
And I'm going to switch to Swedish again. Hoppas att ni tyckte att det här var intressant. Vill ni veta mer så tveka inte för en sekund att kontakta oss. Så berättar vi gärna mer om hur det här kan hjälpa just er. Så tack för den här gången och hej då!
Bye bye, thank you guys.